Okay, so we're still talking about the pentose phosphate pathway. We've gone through the initial oxidation steps. That is, starting with glucose 6-phosphate, we oxidized it to the lactone form. Right? By oxidizing this hemiacetal at a classic alcohol dehydrogenase-like reaction, we create a carbonyl, but since there was already an oxygen, that's a cyclic ester or a lactone. What's the purpose of that? What do we get out of that? What?
You remove stereochemistry.
Well, we remove stereochemistry. What else is the purpose of that in the pentose phosphate pathway? Hint, hint, hint. What are we doing the pentose phosphate pathway for? To make NADPH, right? One of the purposes of the pentose phosphate pathway is synthesis of NADPH. So this is the first reaction where we actually made NADPH. Now, if we go back, let's see. This is where I want to go. Let's see, if we go back to here, right? So we made our NADH, then we opened up that chain, right? And then we oxidized the hydroxyl of carbon 3 of the 6-phosphogluconate, creating out of it a carbonyl, and creating out of that a possibility of decarboxylation. So let's go back and consider that. Right? The 6-phosphogluconate dehydrogenase, it's our second NADPH forming step. Forming would be the word I was looking for there. So we oxidized this, hydride transferred NADP, creating the NADPH. That creates a carbonyl. Right? So here's our carbonyl, but here's a site alpha to the carbonyl. If we have a site alpha to a carbonyl, what can we have? A carbanion. Since there is a carboxyl group there, that creates the prime opportunity for decarboxylation. Electrons from the oxygen come back here to make carbon dioxide. This has to do with language, but if this whole thing is leaving and taking the electrons, it's this that's acting as the leaving group. Right? There was one answer that sort of confused that on the short answer. So it's actually this whole thing is acting as the leaving group because it's taking the electrons. Remember, the leaving group is the thing that takes the electrons. So this whole carbanion acts as the leaving group. It is protonated, and we get the ribulose 5-phosphate. So that's where we were on Wednesday. Is that correct? We'd gotten to that step. True? Okay. Jordan doesn't look like she's fired up about the day. Okay? So, now we are here. And so now we have to start this process of reorganizing. We started that, didn't we? The process of the isomerizations, creating a pool, an equilibrium pool of pentose phosphates. Right? We've got two different reactions, a ribulose 5-phosphate to ribose 5-phosphate, a ketose to aldose isomerization. What did we say about that? When have we dealt with ketose to aldose isomerizations before, or aldose to ketose?
Glycolysis.
Glycolysis, right? Glucose 6-phosphate to fructose 6-phosphate. Glucose is the aldose. Fructose is the ketose, right? So in that reaction, what was the other reaction? Yeah, DHAP to GAP. The dihydroxyacetone phosphate, it was the ketone form. The glyceraldehyde phosphate was the aldehyde form. And what was characteristic of those reactions? Enediolate intermediates, right? So the mechanism of this exactly parallels the mechanism of those other two enzymes we've already talked about. Okay? It's an example of biological systems being as conservative as possible, right? Reusing enzyme forms and enzyme mechanisms rather than recreating the wheel every time. Okay? Now this one, we said it's the ribulose 5-phosphate epimerase. We went from ribulose 5-phosphate to xylulose 5-phosphate. What did that involve?
Carbanion.
Right. A carbanion. You created a carbanion here by deprotonating it from one side, and then you reprotonate it from the other side, because as soon as you create that carbanion, an atom with an unshared pair of electrons adjacent to an sp2 hybridized atom will also go sp2 so that it can participate in that pi system. Once it goes sp2, you lose stereochemistry, and so you can create the stereochemistry from either side. Okay, so is that where we were on Wednesday? That all sounds familiar as I'm talking about it. But given that I've been doing this for a long time, it's all starting to sound familiar anyway, so I can't always remember what I've said. You know, when you're a young faculty member, day to day runs together. When you're an old faculty member, year to year runs together. It's just kind of the way it goes. So, questions? Are we all happy with where we ended up on Wednesday? Okay. So, now let's start reorganizing this. So we're going to do transketolase to transalkylase. So now we have a pool of 5-carbon sugars. Ultimately, we want to reorganize these 5-carbon sugars into things that can go back into glycolysis. Because the pentose phosphate pathway, if we look, right, if we go back and look at the pentose phosphate pathway the way we laid it out originally, right? You can see we come out away from glycolysis. We get this 5-carbon pool of 5-carbon sugars, which then we reorganize into things that can fit back into glycolysis. It's a reason why does anybody know what the other name for the pentose phosphate pathway is? The other name for the pentose phosphate pathway, and you don't have to turn the thing. Gee, I can't write it down anyway because there's no chalk in the room. Is the hexose monophosphate shunt. Right? The other name for the pentose phosphate pathway is the hexose monophosphate shunt. And so it's just this sort of side reaction that leaves glycolysis and comes back. So somehow we've got to get those 5-carbon units reorganized into 6 and 3-carbon units that we can fit back into glycolysis. Okay, so the reactions we're talking about now are going to do that. And that's where we have to think about the stereochemistry, or not the stereochemistry, the stoichiometry a little bit, right? How do we get 5-carbon things to evenly fit into 3 and 6-carbon things? Well, at least we must have a multiple of 3 of them. That would be 15 carbons. And out of 15 carbons, we could make 2 6s and a 3, right? So we've got to have at least 3 of these, which means we had to start with at least 3 glucose units entering the pathway. I think it's usually easier to think about 6 glucose units entering the pathway. 6 glucose units enter the pathway. We lose 6 carbon dioxides. So how many, if 6 glucoses go into the pathway, how many carbons do we have? 36. And if each one loses a carbon dioxide, that's how many carbon dioxides lost?
6.
6. So how many carbons do we have left now?
30.
30. And so it's easy to see how we can distribute 30 carbons in this 5-carbon pool and still get out of it essentially 5 6-carbon units. right? We can take 6 5-carbon sugars, and out of that make 5 6-carbon sugars. So really we're making this NADPH at the expense of 1 glucose, right? We're losing 1 glucose's worth of carbon in that kind of stoichiometry. Does that make sense? Okay, so let's go back to where we were and look at the layout. SRAM. No, I'm right here. Okay, so we'll talk about this pathway, and then we'll go back and we'll talk about the mechanisms of a couple of these enzymes. So, actually I want to start with transaldolase. I want to go to number 7 on my made-up figure. I'm going to skip 6 and I'll go back to it. Transaldolase. Well, let's see. If we take the trans off, what do we have? Aldolase. What did aldolase do? Yeah, the enzyme aldolase in glycolysis. What did it do? Right, so it did a reverse aldol condensation. It did a reverse aldol reaction. That is, if you had a carbonyl sugar, that became the alpha carbon, you could break the between alpha and beta, right? Okay, what transaldolase does is it does that where you get this carbanion. But then instead of just pronating that carbanion, it uses it as a nucleophile to attack the carbonyl of another aldehyde sugar. So wherever the carbonyl is, you go over 1 carbon, you break that bond, and essentially you're transferring that group to an aldehyde sugar. So in this case, we're taking a 7-carbon sugar, which I didn't show us making, a 7-carbon sugar, and taking 3 carbons off of that and making a 6-carbon sugar. So mechanistically, it's very closely related to the aldolase we had before. In aldolase, if this unit is a base, the acid is the hydrogen ion. In transaldolase, if we remove this unit as a base, its acid target is the carbon of that carbonyl. Right? So this is another one of those, today on the soap opera, the role of, right? In aldolase, the role of acid was played by the hydrogen ion. In transaldolase, the role of acid is played by the electrophilic carbon of an aldehyde sugar. And we'll show the mechanism of that here in a second. Okay? Now, in transketolase, we've got a slightly different arrangement. Okay, so here on my transketolase slide, let's see if I can get a better transketolase slide, since I'm really talking mechanistically first.